So let's consider two proofs on groups. Two proofs on groups. So the first one demonstrates your ability to invert things on the group. And I know this seems obvious. Invert elements of the group. I know this seems obvious because groups have inverses in them, but in math, sometimes you need to be a little tedious and prove every last thing, and that's kind of what proofs are for. So this proves from our very basic conceptions of the basic rules of a group. Associativity, identity, and inverse, that we can always invert actual elements through a process called inversion. So the proof relies on this supposition. Suppose that X has two inverses, Y and Z. Then XY equals XZ equals E. So XY equals XZ. Y of XY equals Y of XZ. Y of XY equals YX of Z. Therefore, EY equals EZ, and Y is equal to Z. Whew. So, this proves that inverses are unique. Because if you have any more copies of a particular inverse, this particular proof applies to XY equals XZ equals XA equals XB, etc., etc., etc. By definition, all of these guys have to be equal to each other because the two inverses have to be equal to the identity. Right? So this is quite a straightforward proof from top to bottom. XY equals XZ is what we're supposing. Right? Two inverses, XY. X is the original number in both cases. Y is one inverse. Z is another inverse. And because it's an inverse times the original number, we get E. We set our equivalence equal. From here, we perform the operation on both sides. Right? Basic math. From here, of course, we get to apply the change of bracket position due to associativity. And then last but not least, we recognize once more that this is the identity element because it's an inverse by its original, as is this one. With the result that Y is equal to Z. Therefore, those particular values have to be the same. Let's look at another proof, which is that in a group G, G inverse is equal to G. Again, this applies for all groups, which can be handy. We start to get a grasp on the basic properties of each group, and these are things that make the individual groups useful. So understanding them helps us understand the groups as a whole. G inverse composition G inverse is equal to E. Okay, don't get confused off the front here. This is just based on this. So what we're doing is we're supposing this particular thing to be true, right? That in a group G, G inverse is equal to G. So here we have G inverse and its composition G. This is just because this is equal to G, right? An initial term in this whole equation could be G inverse equals E, which is just the rule of inverse. Right? From here, G inverse, composition G inverse. I'm not even going to touch the left-hand side. This is just equal to G composition G inverse. Right? Again, this is just the rule of inverse. This whole thing all over again. Now comes again a basic maneuver. We're going to composition the entire thing by G. G inverse, composition G inverse. That's just this side of the equation over here. Composition G. It's equivalent to, stick some brackets in, G composition G inverse, close brackets, composition G. We just did the same thing to both sides, right? Right, and we can see explicit definition of this when it comes to the definition of the identity element, right? So EG equals GE equals G. Right, we have this ability to compose things. So this is what follows is what I think is the most tricky move, which is to notice that we can use associativity to change these brackets. We can move these brackets over, which is really nice, because that allows us to get G inverse, composition, open bracket, G inverse, composition G equals G composition, G inverse, composition G. Here we again have exactly the rule of inverse. This guy just keeps on coming in handy. And we get G inverse, composition E equals G composition E. This is super great because at this point everything is done and dusted. You have the identity on either side, and you have that G inverse equals G, which is exactly what we were looking to prove all along. For all groups.